So today we will discuss some problem based on thermodynamics. Now see the question number 1. A container with insulating walls is divided into two equal parts by a partition fitted with a wall. One part is filled with an ideal gas at pressure P and temperature T, whereas the other part is completely evacuated. If the valve is suddenly opened, the pressure and temperature of the gas will be. The first option is P by 2 and T, second option P by 2, T by 2, and third option P and T, and the fourth option P and T by 2. See. So as per the question first, this is your insulated wall. This is a container having insulated wall. Insulated wall means heat cannot transmit or cannot interact from inside and outside. Whatever the heat will be here, that will remain same. And in this container, this is let a partition. This here completely evacuated means vacuum, and here gas is there, and this gas is at pressure P and temperature T. First of all, since this is a complete vacuum, there is no pressure from inside, from this side. So as soon as this is open, so gas will occupy complete volume. Since there is no pressure from this side, the gas does not have to do any work from here to here. So that is the case of free expansion. It is just like a free expansion. In the free expansion, work done is zero, and since it is completely insulated, there is no change in or no supply of heat. So as per the first law of thermodynamics, this is our equation. Here, delta Q is 0, delta U, work done is also 0. So change in internal energy is 0. So no change in internal energy means temperature of gas remain your constant. Temperature of gas remain constant, but earlier the gas was in the V by 2 volume. Now the gas will be in the total volume V. So volume get double, so pressure get half if the temperature your constant. So pressure of the gas will be your now new pressure your P by 2 and new temperature will be your remain T. So option your first option is the correct option. That is the answer. The pressure will be your P by 2 and temperature will remain as T. Question number 2. Question is given as, during an experiment, an ideal gas obeys a additional equation of state P square V is equal to constant. The initial temperature and volume of gas are T and V respectively. When it expands to volume 2V, then its temperature will be. The first option is T, the second option root 2T, the third option 2T, and the fourth option 2 root 2T. Now see, in this problem, a different relation given, P square V is your constant. P square V your constant. So volume and temperature of this is given. As we know, this is the given expression. Now, from ideal gas equation, PV is equal to nRT. So we can substitute the value of P over here. Now, so that become your nRT by V square into V is your constant. So this will be your T square, and this is your V to the power minus 1 is your constant, this new constant. So now, so from here we can write T1 square by V1 is equal to your T2 square by V2. Now, as per the given expression, initial temperature T, volume V, and the volume when 2V, initial temperature T, volume V. Now when the temperature we have to find when the volume become your 2V. See, T2 square will be 2T square. So T2 will be your root 2 into T. This is the volume. So our correct answer is your option number 2. Okay, the final temperature will be your root 2 T. Question number 3. A monatomic, diatomic and triatomic gases whose initial volume and pressure are same are compressed till their volume become half the initial volume. The first option. If the compression is your adiabatic, then monatomic gas will have maximum final pressure. Second option. If the compression is adiabatic, triatomic gas will have maximum final pressure. And in the third option, if the compression is adiabatic, then their final pressure will be same. And the fourth option, if the compression is your isothermal, then their final pressure will be different. So we have to see the options here. See, as per the expression for adiabatic, PV to the power gamma is constant, and for isothermal, PV gamma is your constant. In case of isothermal, pressure PV, it doesn't matter which type of gas is there. So for all type of gases, if any process has been done isothermally, so if initial stage of any type of gas means dia, mono or triatomic, then the final will be also same for all gases. So as per the option number 4, if the compression is isothermal, then their final pressure will be different. This option is your wrong. Now here gamma. Gamma is your depends on type of gases. For monoatomic gas, gamma is your 5/3. For diatomic, gamma is your 7/5. This is your 1.66, 1.4. Likewise. So what is given here? It is given initial volume and pressure are same. Now compressed volume become your 1/2. See, if I am talking about the monatomic gas, P1 V1 to the power gamma is P2 V2 to the power gamma. So P2 is equal to your P1 V1 by V2 to the power gamma. Now from here, initial pressure is same, volume get your half, 2 to the power gamma into P. This is the expression for pressure. If we are having monatomic gas have maximum value of gamma, so pressure will be your maximum, and then diatomic, then triatomic. So as per the given option, option number 1 is saying if the compression is adiabatic, then monatomic gas will have maximum final pressure. So this statement is the correct. So our correct option is option number 1. So this is the correct option. Question number 4. A monatomic gas initially at temperature T1 is enclosed in a cylinder fitted with a frictionless piston. The gas is allowed to expand to the temperature T2 by releasing the piston suddenly. If L1 and L2 are the length of the gas column before and after expansion respectively, then T1 by T2 is this we have to find. The first option here, L1 by L2 to the power 2/3. Second option, L1 by L2. Third option, L2 by L1. And the fourth option, L2 by L1 to the power 2 by 3. So as per the given question here, it is given a monatomic gas initially at temperature T1 enclosed in a cylindrical cylinder fitted with a piston. Let this is any cylinder fitted with a piston, and right now the temperature of this is your T1 and length of this your let L1. It is given as. Now it has been expanded to the temperature T2 and then the length become your L2, and the expansion is like that suddenly. So whenever sudden expansion is there, sudden expansion means expansion indicate adiabatic process. Adiabatic process. So in sudden expansion here, the piston goes up to here. That piston goes here, then the length become your L2 and temperature your T2. So we can find the relation between the volume and temperature in adiabatic process. So as PV to the power gamma is constant in adiabatic process, and from ideal gas equation P written as nRT by V, gamma your constant. Then we can write TV to the power gamma minus 1 your constant. Initial temperature T1, initial volume V1 means length L1 because area is same, L1 to the power gamma minus 1, final temperature T2 and length here L2 to the power gamma minus 1, like this. And then we have to find T1 by T2 value. See, T1 by T2 is L2 by L1 to the power gamma minus 1. And since the gas is your monatomic, for monatomic gas, gamma is your 5 by 3. L2 by L1, 5 by 3 minus 1. So this will be your L2 by L1, 2 by 3. So T1 by T2 is equal to your L2 by L1 to the power 2 by 3. Our correct option, your option number 4 is the correct option. Question number 5. 1 mole of a gas expand obeying the relation as shown in the PV diagram. The maximum temperature in this process is equal to, the first option is given P0 V0 by R, second option 3 P0 V0 by R, third option 9 P0 V0 by 8R, and the fourth option 9 P0 V0 by 4R. Now see the PV diagram. In the PV diagram, the straight line is given. This is your PV diagram, straight line. And this straight line, at a certain instant, the volume is given here, V0, P0, and here the volume and pressure is given 2 P0, V0 and P0 by 2. This is given. So we can say here 2 V0 and this is your V0, pressure P0, and this is your pressure, and they are asking the maximum temperature in this process. So first we would like to write the process equation. See, process equation, because this is not our well-defined process, we will write the equation of this line, by using PV is a straight line, y is equal to your mx plus c. M in the slope, this is a negative slope. So see here, this is your P0 by 2, this is your V0. So minus P0 by 2 V0. This is the slope, this by this, and now V plus intercept. If we are talking about the intercept, so let that intercept here any value C. C is any constant. This is the process equation. Now, from this process equation, we can substitute the value of, or we can get the value of C also. Another equation, your ideal gas equation. For ideal gas, as we know, PV is equal to your nRT. Any value we can substitute. See, from first and second, pressure value I am putting here, minus P0 by 2V0 into V plus C into V is equal to your nRT. For maximum temperature, I am doing dt by dV must be equal to 0. Do this one. Differentiate. This is your V square minus 2P0 V by 2V0 into dV plus C into dV nR dt by dV. So this value we are putting as 0. So that gives us dt by dV 0. That gives us V is equal to minus C plus CV0 by P0. So this is the volume at which we are getting the maximum temperature. Just substitute the value of this V in any of the expression, we can get the maximum temperature. See, on substituting, this is the equation number 3, this is equation number 4. Now, from third and fourth equation, see, from third and fourth, substitute the value of V minus PV0, P0 into V, P0 into V, see from here, P0 by 2V0 into V, V is your C, V0 by P0 plus C into V, CV0 by P0 is equal to your nRT. Now simplifying, P0 P0 cancel, V0 V0 cancel, minus C by 2, this is C, C by 2. The C square V0 by P0, this is your nRT. So here temperature value we are getting your this much. Now from this we have to eliminate the value of C and nR, value of C and N, and for that purpose we will use this ideal gas equation. See, now when we are substituting the value of this, check it here. This is the maximum value of V, or you can say this is the V at which we are getting the temperature your maximum. So T is equal to C square V0 by 2P0 nR, and now see from here C value we will determine. Now substitute the value of V. As V is 0, when P is 0, we can get the value of relation between this, and here we can get the same relation here. Now see, from equation 1, P is your minus P naught by 2 V naught V plus C. If we are substituting the certain value over here, see, P is your P naught, V is your V naught, then we can get the value of C. See, P naught is equal to your minus P naught by 2 V naught into V naught plus C, and this give us C is equal to your 3 P naught by 2. Now this value of C we can substitute here, and number of moles is given your 1. So T. So T maximum is equal to your V naught by 2 P naught R, V naught by 2 P naught R into C square. This is your 3 P naught by 2 square. So T maximum is 9 P naught V naught by 8 R. So 9 P naught V naught by 8 R. This is the correct option. So option number 3 is the correct one. So hence answer 3 is the correct option. Question number 6. The relation between internal energy U, pressure P and volume V for an ideal gas in an adiabatic process is given by relation U is equal to A plus B PV. Find the value of adiabatic exponent gamma of this gas. So first option is given B plus 1 by B, second option B plus 1 by A, third option A plus 1 by B, and the fourth option A by A plus B. So as per the given question here, U is given as A plus B into PV, and we want here this value of your adiabatic exponent. See, U is the potential, U is the internal energy. As per the ideal gas equation, PV is equal to your nRT. So that we can write from here, the U is equal to A plus B nRT. Now change in internal energy du is equal to your, that can be written as B nR dt. And as we know, change in internal energy can be written as N CV dt. So from this expression, if we are comparing first and second, from first and second, CV is equal to your B into R, then CP. CP is, as we know, R plus CV. Which one your 1 plus B into R. So gamma is equal to your CP by CV, which your 1 plus B by B. So this is the adiabatic exponent. So our correct option is your option number 1, B plus 1 by B. Question number 7. Suppose 4 mole of an ideal gas undergoes a reversible isothermal expansion from volume V1 to volume V2, where at temperature find the entropy change of the gas. So entropy change is written as change in energy per unit or per degree temperature. So it has been changed from volume V1 to volume V2. Now total heat supply Q is equal to delta U plus work done, and delta U, so here temperature your T given here constant, so work done we have to calculate. Work done is equal to your P into dV. and isothermal expansion from volume V1 to V2. Isothermal expansion, the work done written as nRT ln V1 by V2. So, and delta U is equal to your 0. Now here delta Q. Delta Q now it will be your nRT ln V1 by V2. So entropy. Entropy is your delta Q by T, which is nR ln V1 by V2. Now value of N is given 4 mole and R is the gas constant here and volume is given here V1 to V2. So now we can substitute the value, then we will get the option 23 joule per Kelvin. Hence option number first is the correct option. Now see question number 8. Question is given as a cyclic process for 1 mole of an ideal gas is shown in the diagram. The work done in AB, BC, CA respectively. The first option is your 0, RT1 ln V1 by V2 and RT1 minus T2. Second option R and T1 minus T2 R RT1 ln V1 by V2. Third option 0 RT2 ln V2 by V1 and RT1 by V1 V1 minus V2. Fourth option 0 RT2 ln V1 by V2 and RT1 minus T2. Now see the VT graph, cyclic process. So the process is like this. This is your cyclic process. VT graph here given and the graph is like this. This type of process is given A to B, B to C and C to A. A to B, B to C and C to A, and the temperature at A is T1, volume your V1, T1, volume is your V1 and temperature at B is T2 and volume is your V2. Now we have to find the work done in the process AB, BC and CA. First of all, work done in AB process, that is 0 because this is your isocoric process. Isocoric process, volume your constant. In this process volume constant, so work done will be 0. B to C. BC is your isothermal process. Isothermal process, work done in BC is your nRT, so nRT2 ln V2 by V1. V2 by V1. This is the work done in B to C. And C to A, straight line passing from the origin. V is proportional to T, so that is your isobaric process. This is your isobaric process. Isobaric process means pressure your constant. So work done in C to A, P V1 minus V2, that is also written as NR T1 minus T2. So these are our relation related to work done. So in the first WAB 0, second nRT2ln V2 minus V1, and the third nRT1 minus T2, and the value of n 1 mole of gas is given. So correct option is your answer number 4. Now see the question number 9. Two cylinders A and B fitted with a massless piston contains equal amount of an ideal diatomic gas at 300 Kelvin. The piston A is free to move while that of B is held fixed. The same amount of heat is given to the gas in each cylinder. If the rise in temperature of the gas in A is 30 Kelvin, then the rise in temperature of the gas in B is first option 30 Kelvin, second option 18 Kelvin, third option 50 Kelvin, and the fourth option 42 Kelvin. In this question here, there are two containers in which one is your piston A, which is free to move, and B. This is your fixed. This is your free. So what is the difference? This is the gas here. What is the difference here? Whenever we are supplying heat, since it is your fixed, volume constant, V your constant, and here pressure is constant. So whatever heat has been supplied, it is given same amount of heat has been supplied. So that heat Q is equal to N Cp delta T. And here what is the rule of Q? Work done will be 0 N Cv delta T. Now they are saying the rise in temperature of the gas in A is 30 here. So N Cp delta T or 30. This is Q. Their same Q we can put here. So 30 N Cp into 30 is equal to N Cv into delta T. N cancel, and as the gas is given here, this is your ideal diatomic gas. So delta T here, Cp by Cv into 30. For diatomic gas, Cp by Cv is 7 by 5 into 30. So delta T is your 42 Kelvin, and 42 Kelvin is the option number 4. So answer is your fourth option. Question number 10. A monatomic gas initially at pressure P, gamma for that gas is 5 by 3, is suddenly compressed to 1 by 8 of its volume adiabatically. Then the pressure of the gas will change to first option 24 by 5P, second option 8P, third option 40 by 3P, fourth option 32P. So gas has been compressed adiabatically. So as we know, for adiabatic expression, PV to the power gamma is constant. So P1 V1 gamma is equal to your P2 V2 to the power gamma. Initial pressure your P, and now the volume has been changed. Volume has been changed 1 by 8 of the initial volume. So 1 by 8 of V to the power gamma. So P2 is equal to your P, and then 8 to the power gamma, and gamma value for this is given your 5 by 3. So this is your 2 to the power 5 into P. So P2 is equal to 32P. So our correct option is your option number 4.